Good morning, everybody. Apparently, I discovered this morning that I finished last Tuesday, so no class today, bye. No. Yeah, some of you are very happy. No, this is a good thing, right? Because we've got today and tomorrow to prepare for the exam, right? So, I don't really know what to do here. Do you want to ask questions first? Do you want me to just kind of start summarizing? Like, what would help you the best right now? I know like chapter 8 homework is like the big thing because that's due when? Tomorrow? Right? So we can go over chapter 8 homework. Before you put your hands up in the air, we need to deal with chapters 7 and 8 because I know there's all kinds of anxiety over that, right? There's remembering chapters 5 and 6, which is anxiety-inducing in and of itself, right? So we've got to have some time where we're reviewing like Newton's laws, free body diagrams, how to do all that kind of stuff. There's the chapter 7, 8, there's chapter 8 homework. There's talking about the cheat sheet if you want to. There's a lot of things that kind of have to all fall into place before Thursday, right? Okay. So this is choose your own adventure. What do you want to do? Do you want to focus like on the energy stuff right now? Go back, start reviewing Newton's laws? Do you want to do Newton's laws tomorrow? Like what's your, does anybody have an opinion? Cheat sheets, talk about cheat sheets maybe. Possible things to put on cheat sheets. Now, of course, I'm always hesitant to tell you what to put on a cheat sheet because every brain is different. But since it's fresh and kind of new and you're working on it right now, let's talk about chapter 7 and 8 cheat sheet, right? This is not going to be a guarantee of a complete list of equations. You are going to have to go through and do your due diligence to make sure, right, that you have everything that you want. But as far as my brain is concerned, chapters 7 and 8 have exactly the same toolbox, and the list of equations is pretty short. It all starts with that one. And then there's just parts that we have to remember, right? It's always the correct application that's the sticker. But there's kinetic energy, energy associated with motion. There's potential energy from gravity. And then there's potential energy from springs, sometimes called elastic potential energy. Okay? That brings up Hooke's law, which often has a minus sign in it, but I generally don't write that minus sign down because the minus sign would be there if I had vector arrows over the tops of things, and I don't. How do we write down work other almost all the time? Force times distance, but technically it's force times distance. It's the dot product, right? I would write down cosine theta there, not so much as a hard and fast rule, but as a reminder to me that I've got to check the directions of the force and the distance, right? Because if this is kinetic friction, then we know that the work's going to be what? Negative, right? So that cosine theta, to me, says check force and distance. Now, for you, it might be meaningless. It might be more hard and concrete, in which case you might want to just put plus or minus FD, right? Which again, might be a reminder that's look, check to make sure is the work positive or negative, right? If you've got a force opposite the direction something's going, we got to remember to put that negative sign on it. And again, here you kind of have to be careful. If your force is at an angle compared to the direction you're going, you have to find the component that points in the same direction. So whatever it is you need to do to remind yourself, dot product, FD cosine theta, plus or minus FD, whatever it is to remind yourself that with work, you do want to check. Is it positive, negative? Am I lining everything up? Do whatever it is you need to do. Here, I'll write them all down. I don't care, right? So, all right. Oh, that just looks weird. Take the plus or minus off. Equals F dot D. There we go. Now I feel much better because I've got it as a dot product. Maybe you don't feel better with it being a dot product. There was a little thing that snuck in almost tangentially. That was power, which was the work per time or the energy per time. You, of course, can put units on all of these things, but everything on the screen except power has units of what? Joules. And then the units of power would be watts, right? So it's a joule per second. So, maybe you need to have all the units. I've been around them enough. I tend not to write them down anymore, which is bad of me. Am I missing anything in the toolbox for chapter 7 and 8? Anything you ran across that confused you, like in the book or online or... So what's not in this toolbox is how you use it, right? So maybe you want some lists in there with you, right? So that you can, trigger your mind. Like, what does the visualize look like? When you're doing that first step of visualization, what 3 things do you have to define to be able to even apply the first equation? Initial, final, and 0 for gravity, right? Where's the 0 for springs? Wherever the spring is not stretched or compressed, the resting position of the spring, right? That 0 you can't change. But gravity 0 you get to pick, right? So you've got to have those 3 things defined somehow, some way. You can, of course, still write down things that you know, things that you don't know, all that kind of stuff, but you have to define those 3 things.
When you said 0 on the resting position of the spring, you're not talking about the ground, you're talking about on top of the spring.
Wherever the spring is neither pulled out or squished in. It's wherever a spring would naturally rest if it's left alone.
How do you know when you use the spring formula or Hooke's law?
So Hooke's law is not about energy. The force is in newtons, right? Mm-hmm. So you use Hooke's law to find like a spring constant. Okay. You had a couple of homework problems where you had to get the spring constant. They told you the force. They told you how much the spring got compressed or stretched. And so you could then calculate the spring constant. That's typically where it's used. If you need to know the force that a spring is exerting, use Hooke's law, right? But energy, right, in joules, that's 1/2 kx squared. So look at the units. Good questions. All right. So that's like key in the visualization step. Of course, you're going to be doing other things. You're going to be drawing a picture? Mm-hmm. Probably. You're going to be making a list? Mm-hmm. Maybe. Like there's other things in there, right? But you can't get any traction into the problem unless you do those 3 things. All right. So then in the strategize. In the strategize, you're doing the work other plus energy initial equals energy final. And what questions do you have to ask for each one of those things? Like work other, what's the question? Are there any forces that are not gravity or springs? And how do you know gravity or springs you don't have to put into work other? Because we have energy equations for them, right? Got potential energy of spring, got potential energy of gravity. Those don't show up in work other. If it's anything else, it goes into work other. If it's friction, kinetic friction, you know it's going to be negative work other, right? If it's propulsion, it's going to be positive work other, that kind of stuff. What questions are you asking for this energy initial term? Like, what are you trying to find out about energy initial? Kinetic or potential of any kind, right? So kinetic, is it moving? Potential gravity, is it at 0, right? Spring, Again, is it at 0? Like, what's the spring doing? If there's no spring, you just everything's 0. So again, those are the same questions over and over again. The answers will be slightly different depending on the problem, but you're asking the same questions consistently for every problem. And then your do it step. Not much to say there. It's math, isn't it? The strategize step, you're going to be sitting there. Sometimes you'll get the equation written down, and then you're like, wait, what do I need to solve for? Or, wait, so you had a homework problem where a block was sliding down and hitting a spring. And I think the problem asked for how far did it slide down the slope? Well, if you set up the problem correctly, that doesn't enter anywhere into your equation. You've got an h, but you don't have the distance down the slope. And so you have to strategize a little bit more and realize, oh, well, if I can find the vertical height, I've got a triangle and I've got an angle, I can find the hypotenuse of that triangle, right? So it takes that extra critical thinking step to realize, okay, the thing I'm solving for, the thing that they want the answer for isn't directly in my energy. Energy is a step to get there. So those things, that's indicative of pretty much any physics problem. And then the fourth step, check it. Which, if you have time on an exam, if you're answered all the questions and you look up and you got 5-10 minutes left, which is, Mr. Balogh, that's funny, then you can go back and start trying to maybe see if it's reasonable, do some order of magnitude, maybe see if there's a different way to check and see what's going on. I understand that we train you to check it by getting green boxes, which is unfortunate. No green boxes on the exam. Would it be extra cruel or nice if you came into an exam and it turned green or red every time you put an answer in?
Do we get to change it if it's red?
Yeah.
Oh, that'd be nice. If you left it where it stayed red and we couldn't change it,
Then it would be, that would be terrible.
everybody would focus on it.
One of the things that we do that is very bad in this department and in this modern age of teaching with these online homework systems is that we train you in these online homework systems, and you get used to this kind of instant feedback, right or wrong, and then we bring you into an exam and it's like no feedback, right? What you know, what you don't know. I really wish I could give you questions, right, in the same format that you've been studying the whole time, right? But technologically, we just can't do it. So, but I often wondered what would happen if we did that, and like, what would happen if you kept getting it red? Would you like burn all your time trying to get the first one to turn green, right? Like I guess it depends on the individual. Anyway, all right, I digress. So, was there anything that cropped up in the homework? Anything like other equations that maybe you ran across? Or ideas maybe that I'm missing here? I don't remember everything perfectly. Does it seem like a lot or not as much as you remember? Yeah, it seems so like small and concise on the screen, but there's a lot going on in there, isn't there? And so, but even then, I feel like the other one is worse, chapters 5 and 6. Because chapters 5 and 6, what's the toolbox look like? Huh?
Honestly, that one was too bad.
That's kind of it, isn't it? Okay. Can't forget fun. Right? Like, there aren't a lot of equations in this toolbox, but this was like the hardest math part of the. Am I wrong? Do you guys is the math harder in 7 and 8? Is
I
it?
feel 7 and 8 were
7 and 8 were harder?
Yeah.
Interesting. I'm losing my touch. I hate Newton's laws. They just generate things, and I don't like having to solve it. You kind of liked it?
Yeah.
Each to their own. That's fine. I'll stop making comments about it. Right? Oh no, my recording stopped. Start. There we go. So I mean, that toolbox is really deceiving, though, isn't it? Is it safe to say that, like, maybe it isn't. I personally feel like the process is easier to follow in energy. Initial, final, zero, write down a single equation, and then there's some math, figure it out. All that kind, like that algorithm to me seems like an easier algorithm to follow. This algorithm over here, this requires like creativity and the ability to draw and identifying forces and finding components, and there's geometry and there's trig, and like there's just, I don't know, there seems like there's a lot going on there that this toolbox doesn't, say anything about. So short of like just copying down every homework problem, what could you put on a cheat sheet to help you during the exam, to jog your memory? The picture that just immediately jumps into my brain, right, is this one. Like if I just had something, and it really doesn't matter what these forces are, but like if I just had something that's reminding me, oh yeah, right, I've got angles, and I know that angle there, and this one's going to be, this is mg, and so this is mg sine theta, mg cosine theta. I've got a normal force. I might have maybe there's a force acting up or down. I don't know. But like that picture right there, it may not be exactly the picture that I need for the problem I'm solving on the exam, but it's helping my brain orient in that particular moment to the problem at hand, right? And I'm going to rely on what I've learned, and I know you feel like you've learned nothing, and I know you all feel like you have imposter syndrome or something, and because you're not, I'm not supposed to be here, I don't understand what's going on, and if anybody found out, I'd fail. No. I shouldn't say things like, imposter syndrome is normal in physics class. Everybody feels like, I still feel like an imposter. Right, because there isn't I couldn't possibly know all of physics, right? And the only way I come in here and look like I know what I'm doing is because I looked at it this morning, right? Okay, and I've done this a lot, right? So like, again, this is your first time through it, and so we need to acknowledge that you feel uncertain, shaky, like you don't know anything. You know plenty. You believe it or not, you've learned quite a bit. And so you need to hold on to the fact that your brain knows how to work it, and you've got to dig it out at the right time. So anything you can do to help your brain remember in that moment, right? Now, one of the things I did for you this time through on the exam that I should have done the first time, and I apologize, every question has the topic on it, right? So question number whatever, right? And then it gives the question, and then in small italic writing at the end of the question, it'll say topic, circular motion, or whatever, right? Okay? And so you can look at that topic. I've already given you the topic, so you could even organize your cheat sheet like by topic if you wanted to, right? 7 sections of your cheat sheet, everything I know about circular motion, Newton's second law, energy, whatever, right? Okay, so then you can like, oh, this is circular. Okay, I'm looking at this part of my cheat sheet, right? And again, you had an exam before, right? So anytime you can save where you're looking at the problem and then looking at your cheat sheet, right? The saving time from like, where is it on my cheat sheet, right? Having a good organization. Organize it by topic or by chapter. It's up to you, right? You know your brain, well, maybe you don't, but you're learning how your brain works. See what that. I mentioned circular motion because that was the other thing about the toolbox over here, right? There could, so like, we had the vertical circle example kind of things, right? So you can get like a real quick thing in there. This isn't complete, right? But acceleration be that way, acceleration be that way. If you had a problem where the car was going over the top, right? So you can remind yourself normal force, mg, acceleration is still towards the center. It would still be down. So again, you're looking for things that will remind you that you can recall sort of how to set it up. But again, the algorithm's there, right? In the visualize, key thing is the free body diagram, isn't it? You've got to get that free body diagram drawn. The question, the algorithmic question you're asking is, what's pushing or pulling on the object or objects in my problem, right? If you can name an object, then it's exerting a force. The forces we have are friction, tension, gravity, normal. And then maybe some other force, like if they say that the penguin is being pulled up the slope by a worker or whatever, right? Okay, you can just label those F, right? So the key thing about tension is that it can never, what can tensions never do? Push. A tension is a pull-only force. Normal forces, why are they called normal? They're perpendicular to surfaces of contact. So you know if some things are touching each other, there's going to be a normal force. Friction's always perpendicular to the normal force. It's in the surface, the plane of the surface of the point of contact. So again, maybe those definitions help you or not, right? So I'm looking at the topics list here. I'm seeing if I'm missing anything on my cheat sheet. So we've got circular motion. I've got it there. You could, it might be handy, because I won't give you an equation, right? But it might be handy to have the centripetal acceleration, speed, right? That was from chapter 4, I think. And then other topics are conservation of energy times 2. That means that there are 2 conservation of energy problems on the exam, right? 2 out of 7. And that's 2 out of 7 coming from this section right here. Newton's second law. So something along these lines. Could be connected objects, could be not. Newton's law is conceptual. Okay. So there's 3 Newton's laws, isn't there? Only one of them produces math. What are the other 2? First and third. What does the first say? Forces or pushes or pulls, right? Okay. And that objects want to keep doing what they're already doing unless they're pushed or pulled, right? It's the law of inertia. And it kind of sort of helps us figure out what mass is, but not really. And then the third law, it's the song, right? It's the song. So no singing out loud in here on Thursday, right? No singing zone on Thursday. But being able to apply Newton's third law, understanding that when objects interact, the forces are equal and opposite. But also to not fall into the trap of a Newton's third law pair. What do I mean by that? So, how many objects are required when we're talking about Newton's third law? 2. So, for me sitting here in this seat, I have a normal force from the seat holding me up, and I have the earth pulling me down. Are those Newton's third law pairs, the action-reaction pairs? No. How do I know? There's only one object drawn here. Those forces are applied to only one object. How many objects must there be for Newton's third law, action-reaction pairs?
2.
There has to be 2. So what is the reaction? What's the opposite, equal and opposite force to mg? Sing the song. If the earth pulls on the Mr. Balogh, then the Mr. Balogh pulls on the earth. Where's the earth in this drawing? Nowhere, right? So I'd have to come down here and draw the earth. I mean, it's far away, but it's not, right? And then there would be like an mg acting up like that. These two forces right here are equal and opposite. Two objects pushing or pulling on each other. Okay? So where is the reaction, the Newton's third law reaction to the normal force? The song, the normal force comes because of the Mr. Balogh and the ground, the surface of the earth, right? And so where's that? Well, I'd have to draw another picture, right? There's the ground, and then there would be some normal force acting down. These two are Newton's third law action-reaction pairs because there's two objects, right? So Newton's third law can get in, it feels like we're getting into the weeds here, but it's really important to understand. A force only exists if two objects are interacting. A free body diagram, right, is a diagram of how many objects? One, right? And so how do you know that these forces have to be equal in magnitude but opposite in direction, but are not Newton's third law pairs? It's one object, so you know they're not a Newton's third law pair. But how do you know that they are equal and opposite? What is true about me right now as far as Newton's second law is concerned? My acceleration is 0. Why is my acceleration 0?
You're not moving.
I'm not changing my velocity. Direction and magnitude of my velocity are not changing. And so therefore, my acceleration 0, the total sum of forces on me has to be 0, and so I need to make sure that whatever up I have is my down. Now, when I get up from my chair, what must the chair do? It has to push on me upwards, right? I exert a force downwards on the chair pushes up on me with more or less than my weight. Not same. Because if it was same, what would happen? I'd be more of an old man. Less? If the chair was less than my weight, what would happen? Be falling, right? What does it have to be? More. I weighed 175 pounds this morning. So when I push on this chair, what am I pushing with? More than 175 pounds, right? To get my ample bulk going. So, I didn't understand a word of that, Mr. Balogh. Okay, go back to the YouTube, listen to it again, try to remember what you saw. Those of you that aren't here that are watching on YouTube, you're out of luck, right? But the point here of taking you through that exercise, how many objects are required for Newton's third law? Two. If an object is going to change its motion or accelerate, the forces on it must be in order for an object to have acceleration, what must this net force be? Not 0, right? The only way that an object will have no acceleration is for it to have no net force. We're talking about Newton's second law here, right? But I started with Newton's third law. There's a trap. This is what I've been trying to teach you just now. There's a trap. People tend to conflate or confuse Newton's third law and Newton's second law together. Newton's second law applies to how many objects? One, right? We might have several objects connected together, but we apply the free body diagrams in Newton's second law, we apply them one at a time, right? But Newton's third law is how many objects? Two. Sometimes I wonder if reviewing just makes you more anxious. What else have we got? I was looking at the thing. Conceptual. Power. I've got power down here, right? So I'm going to be asking you a question about power. Be ready to calculate a power. Power is work per time. I think the other one, if I'm remembering correctly, was force times velocity. Technically a dot product, but you can just make sure they're going in the same direction. And then a question, vector dot product. So this, do you remember last exam I gave you just like a straight up vector math problem? It was this vector plus that vector minus another vector or something like that, right? So exactly that same style of problem, but here's vectors, find their dot product. So just show me that you know how to do a dot product. So when it comes to the vector dot product, woo, those are the building plans. What's going on? Come back. All right. So we got that. We got that. Vector dot products. How do I do a dot product? Let's see. So a dot product between two vectors can be magnitude A, magnitude B, cosine of angle between them, or AX BX plus AY BY plus, I'm not going to give you Z's, I don't think. Hope I didn't. So those are the two methods for doing a dot product. I can use the magnitudes of the vectors, magnitude A, magnitude B, angle between them, cosine of angle between them. Or if I know the components, I take the x's, multiply it together, take the y's, multiply those together, and then add at the very end. When you're done, should you have a vector or a scalar for an answer? It should be a scalar. So don't give me a vector when you're done, right? Some students can't help, like, put direction on it. No, there's no direction on it. It's just a number, okay? So just having those definitions down might be worth it. What am I forgetting for cheat? What would you put on your cheat sheet besides this stuff? Examples? Sure. No, yeah. Again, I like it that you make your cheat sheet because then you know where things are on your cheat sheet, right? And you can quickly find where things are. So make sure that you, unlike me right here, that you actually label what these are. Chapters 8 and 7, energy, dot product. Chapters 5 and 6, Newton's laws. I didn't write down any conceptual information there. You might want to, right, just to remember maybe the definitions of Newton's laws, that kind of stuff. I think that's a pretty good review. Like of just sort of an overall, overarching idea. And it's a lot, isn't it? Like a lot of information on this exam. And I know that's like threatening and anxiety inducing and all that kind of stuff. Just remember, you deserve to be here. You've done all the classes you needed to before this class to be here. You've got this. I have tried to make the exam in such a way that you can do a conservation of energy problem in 10 minutes. Notice I said that you can do a conservation of energy problem in 10 minutes. Not me, right? You. So I have methods for testing to see whether or not my exams are too hard, and one of those methods is I take the exam. If I can do it in less than 10 minutes, I assume it can take you less than 70 minutes. So I do them faster. Sorry, I won't apologize for that. I practiced a lot. So will any of the questions be harder than any of the homework questions you've had? No. I've noticed, though, that students, for some reason, try to make problems harder than they need to be. You feel like the problem is, I've watched it, and I die inside every time I see it. They've done the problem correctly, erased it, done it wrong, because they thought that it went too fast. Like it wasn't hard enough, or it wasn't anything like the homework, or whatever, right? Okay? On top of your knowledge, what should you be doing during the exam to make sure that you have time to cover all the questions? Move on if you get stuck, right? Don't be afraid to switch up a question and just move on. Last time I told you when 30 minutes had elapsed, and then I started giving you 10-minute warning every 10 minutes after that. We don't have a clock in this room. Do you want more warnings about time? Less? I know half of you are going to say more, half of you are going to say less. Yeah. Yeah, and then people tell me that that's stressful. Big red countdown. Negative timer. Can I play the Jeopardy theme the entire time? Because some people complain, 30 minutes went by and I'm still working on the first problem, right? Technologically, getting something up on these screens is a little bit problematic, but I'll see what I can do. Maybe I can get a timer up there. Not a timer, just a clock. Just a clock. And then you can decide whether or not you want to look at it. But it's up there, Mr. Bale. I'm going to look at it all the time. Okay, fine. We'll see. Right. Would having a clock during the exam help you? Pace yourself better? Or, yeah? It would help some of you? Okay. The picture I just got in my head is of half the class facing this way and the other half facing that way. I don't want to see the clock. Oh boy. So I'm hoping that with the topics list on there, helping you pace it better, you've experienced one of my exams already, so you know kind of the relative difficulty. You know the format. There's going to be 2 questions per page. It's going to be blank on the back. I want you to try to keep your papers as close to you as possible. Last time I kept wandering around and kind of moving your papers. They were spreading out and I needed you to be tight. What other exam mechanics types things do you need to ask questions or want clarification about so that you have the least amount of anxiety possible on Thursday? Yeah.
I have a question now. The homework was really hard.
Yeah.
I'm really nervous for the test.
Okay.
How will the test compare?
I'm going to try to answer that question, and I'm not picking on you, but I'm going to pick on you. Why was it hard? You don't know? Okay, good. Right? Now, how many of you are in the same boat? It was hard and I don't know why. Do you see how you are not alone? Right? Okay. Now, am I standing up here going, well, you guys are screwed? No! I know that that's what it's like. And did I go out of my way on the exam to like take advantage of that? No. So, it's easier than the homework. Now, in saying that, does that mean you don't have to study? Right? Because easier and harder and the homework's hard and all that kind of stuff, those are subjective words. There's no hard and fast data that we can ascribe, right, to those perceptions and feelings. And I'm not saying they're invalid. They're perfectly valid because it's what you're feeling, right? So how do we get you from, oh my gosh, the homework was impossible and hard, to a level where you're feeling confident that I can apply this stuff, right? You're not going to like, here's the, did I probably mentioned this to you guys. You guys want a hack for this class? Yeah. Study. Read the book. Do your homework. Like, right? That's the hack. And I know you're doing it. I know a lot of you that are doing that. And Mr. Balogh, I'm doing that. And I still feel like I don't know what I'm doing. That's science. Right there. You never feel like you know what you're doing. Because what are you doing in science? By definition, that nobody else has done. Pushing against the unknown. Right? And you're like, but Mr. Balogh, we know this stuff. It's all in the book. Okay, yes, fine. We know this stuff. Right? But you don't know it. This is your first time. And you're learning. That's what learning is. You can't learn something if you don't know stuff. So, Jasleen, how do we get you and the rest of the class from a point where you're like, this was super hard and I don't understand what's going on, to maybe I can do this? It's practice, isn't it? It's practice, practice, practice. Let me ask you a question. We come together in lecture, and I do spend a little bit of time talking about concepts and underlying principles and things like that. I do that because I assume that more than half the class isn't reading the book and needs some help connecting the dots. Would you prefer it that class was nothing but examples? Yeah? Yeah? Because I could do nothing but examples. Just come in and start like in the middle of the chapter. And you know, I've done that before, and sometimes it just, the whole class just gets like bulldozed, right? Because like, yeah, where did this come from? Okay? And so that's why I kind of offload it. But at the same time, I'm only giving you 10 homework questions. Now, I know I could increase the scores on the exams by assigning you 30 to 40 homework questions per chapter. It's bad enough already, isn't it? Right? Okay? And I'm not, don't worry, I'm not going to do that. I just, some people's heart rates just wonk, right? I'm not going to do that. But the problem is, that's kind of what it takes to really dig in and practice this stuff. And I know that there's only like 2 of you in here that are going to be physics majors that might want to do that, right? The rest of you are just trying to make it, trying to survive. So I've given you the 10 to 15 problems I feel like are sort of minimum for survival. Complete understanding is a completely different ball of wax. Am I helping you feel better, Jasleen, or not? Yeah. A little bit? Okay. So what do we do right now to help ground you in the process, say, of chapters 7 and 8? Since that's the homework that's due. Do we want to look specifically at homework problems? Do you want to go through the end of chapter problems and I can point out ones that might be good for you to practice or try? Like, what do you want to do? That? Okay, I want you to know, for the record, you just asked me for more. You just asked me for more. Supervised more.
I feel better doing more practice.
Yeah. More practice will help you feel better. It will. Well, yeah, of course it gets intimidating.
Yeah, I think especially when we have these review days, it's good to have extra problems.
Yeah, well, we're lucky we had an extra review day. I'm kind of worried I forgot to teach something. All right. Let's go straight to chapter 8. Honestly, if you practice chapter 8 and chapter 6, you're already practicing 7 and 5. Because 7 and 8 are the same, they should be one chapter. 5 and 6 should be one chapter, right? So you can focus on 6 and 8, and you will cover everything. Okay, so let's see. I'm just going to click on any of these links. Because what I really needed was a table of contents. All right, chapter 8. Problems. Here we go. Oh! That looks familiar. Let's get these bigger. Let's get this out of the way. All right, so notice I gave you this one, didn't I? Okay. So it says figure 812 for problems 2 and 9. Looks like that's a hyperlink, so I could probably just click it. Let's go down to 9. Okay. You could try this problem, which is going to be very similar, right? It's not really all that explicit, but do you see how 9 has a little line underneath it? If you click on that, it'll take you to the answer, right? So let's concentrate on the odd numbered questions, right? What is the spring constant of a spring? Elastic potential energy compressed. This is going to help you. This isn't a topic that I called out on the exam, right? Zip it, but easy to, it's spring potential energy. 3, Freddy's outstretched hand. How much work? Okay, so now we're talking about work, right? This could be a good one to practice for calculating work, right? What is the change in gravitational potential energy? In other words, what's MGH? Yeah, this 3 is fine. 5. Oh my gosh, 5 looks scary. But it's actually not. And what does SSM mean? Study stupid math. No. Student Solutions Manual. So you could look at the problem, even if it looks scary, and go, okay, well, what they're talking about potential energy, right? What's the value of the potential energy? Well, maybe it's MGH. And then you can go to the Student Solutions Manual. How do you find the Student Solutions Manual? Oh, look, I provided the link right here. Yeah, some of you are now surprised. They've been there the entire time. Okay, so, yeah. Learn how to class. Oh, that looks fun. All right.
On some of the homework problems, why do only some of them have a tutorial?
On purpose. I want you to have one that's got a tutorial, then have one that doesn't, so you're practicing without training wheels. I know there's a lot of crashing that happens there, but skip 7, 9. We did that one. 11. Ooh, 11. Another Student Solutions Manual one, right? So I would like automatically, because I have something that will show me how to do it, I would try this problem and then look at the Solutions Manual, right? 13, another Student Solutions Manual one. So automatically, if it says Student Solutions Manual, I'm gonna try it. I'm gonna look at it. I'm just gonna look at it. It's just practice, right? And when I'm training for a climb, I spend a lot of time falling off the rock, right? Before I complete the actual ascent. So it's okay to keep falling off. 17, doesn't have a student's manual. What does it say? Net force, nah. 19, oh, 19. Yeah. 21. We didn't do anything with pendulums, right? So that'll come back later. So we'll just skip that one. String distance is released as an on. That one's okay, but I would do others that are better than 23. 25. Not 25. Tarzan. Yeah. Sure. You can see that like we're running out of students. Oh! This one has SSM on it, and Mr. Balogh assigned it. Did Mr. Balogh make a mistake? No. I mean, I do make mistakes. Yesterday, I walk into lab for Physics 4B. I'm like, okay, let's start lab. You guys read it, right? And they're like, no. I was like, why not? And they said, because you never gave it to us, Mr. Balogh. You know those dreams? Maybe you don't have them yet, but now you will. Where you've come to class and you didn't know there was an exam, and all of a sudden you have to take an exam and you haven't studied for it? I can tell by the smile some of you know what I'm talking about, right? My dreams have switched to my nightmare yesterday, which is I walk into a room, right? And I'm either forgot to write the exam. It's the same anxiety, right? But I've either forgotten to write the exam or I haven't printed out the thing that we needed. Yeah. So my dreams are based in reality. What is going on? Oh, it's 30. I don't want to do 30. Okay, 31. Oh, okay. Ooh, okay, so wait a second. Could there be a connection between this problem and this problem? Not at all. That doesn't even look similar, right? So again, it might be worth attempting, right? Maybe you don't get the right answer, but you will have practiced trying initial, final, writing down the equation, right? That's a weird hand. This one looks a little bit interesting. All right, maybe 35. I'm going through these really fast. Yeah, 35 is great. 37's got the word calc on it, so let's skip that one. 39, nah. 40, nah. Work done in a system by an external force. A collie dreads is better than a frictional force. Yeah, that's a great one. I like that one. Here's another student solutions manual one. So, but they asked this: the increase in thermal energy of the block floor system. In other words, what's the work done by friction? So like I wouldn't. So this is the part of the problem, right? Like this problem is a fairly good problem, but then you start freaking out over. Oh, we're talking about thermal energy. Don't worry about thermal energy. Not talking about it yet. But there's no way you'd know that, right? Air drag, that's just, again, they're talking about work. So student solutions manual. Lodgepole pines only exist above about 6,500 feet. 7,500 feet, sorry. The weird things that I know. All right. Yeah, 51's okay. 53. Yep. 55. Yep. And now, sorry, Jasleen, I keep picking on you because you asked. These that scared you, right? Yeah. Yeah. Right. Right. And so why is this scary? What did I teach you? A process, right? I wouldn't give you a problem that the process couldn't handle. And yes, I'm demanding that you really kind of know the process to be able to make it through a problem like this one. Where do you put initial? Where it starts. Where do you put final? Where it stops. Where do you put zero? You could put it at the bottom of the dip, but we don't know anything about how deep that dip goes, right? They've drawn a line, haven't they? Right? Okay. They've drawn a line right there to give you a reference height from where it starts. I'd put the 0 at that point. Again, I knew to not put it down at the bottom of this dip because I have no information about how far down that goes. But I do have information about how high, right, it goes. Initial, final, 0. Are there any springs?
No.
Don't have to worry about that. Okay. Your brain is probably still freaking out about friction coefficient. Where's the friction going to be taken care of? Trust the process. What part of the equation deals with the friction? It's work other, because it's not a spring and it's not gravity, and it can deal with it, assuming you get your force times your distance right. And because it's kinetic friction, your work is going to be negative. That's how you do this problem. Follow the process.
What if it was static?
It's not. Don't worry about it. You don't want to know the answer to that question. Cookie jar. No, just even one. Okay. Yeah, 59's great. 61, what's FCP? I have no idea, but it's got bio in it, so bio people rejoice. This particular one, okay, so 62 does have a Go tutorial in it. This one might, well, unfair. It was fair, but so the problem is, right, is the word if. I never liked if-then statements in programming, and I certainly don't like them in my homework problems. The word if implies something about what this block may or may not be doing. If it reaches point B, it will have kinetic energy, won't it? But if it doesn't reach point B, what happens? It stops. Those are two different final kinetic energies, aren't there? So what are you now forced to do? You must solve the problem twice. That's where this one became really hard. Okay? So, and there's a little bit of difficulty in the additional height and finding the distance along L. That's more trig than anything else. But this one throws students because they try to set up just one equation and get stuck. Sometimes I see you writing down like both kinetic energies, one's 0 and one's 1/2. You can't keep those in the same equation, right? You've got to have kind of two different assumptions that you're making, right? Usually what I do is I'll pick one or the other. Like I'll just say, okay, I'm going to assume it makes it, right? And then I solve that problem. And if it's physically not possible, I'm going to get some weird answer. Like I'll get a negative velocity, or I'll get an imaginary number. Something will be really weird in my check it step that doesn't make sense. And then I'll know it's the other case. But if I get a number, if I assume it's moving when it gets there and I get a number, I'm like, oh, okay, then I don't have to check the other case. So sometimes you just commit to one or the other, see what happens, and then make changes as you go. What is going on here? Is that supposed to be an elevator? It is. Yeah, okay. This is not how elevators work. Why didn't I get that one? Oh, because it's mean. All right. Yeah, 65 is great. Unfortunately, you can't get to the Go tutorials if I don't assign them as homework problems. So. 60. What's going on? Oh, no, 67 is okay. Student Solutions Manual, yeah. Yeah, 69's fine. It looks like a chapter 5 and 6 problem, doesn't it? Okay. But it's not, because they're asking you about the total kinetic energy. And when they say total kinetic energy, they mean the kinetic energy of A plus the kinetic energy of B. It's like kinetic energy of the system. Yeah, 71's okay. And of course, what happens as the numbers get bigger? They get harder, right? So at some point, you just kind of give up and you've had plenty of practice until I give you something. No, okay. What God grief, there's 100 and...
That sounds like it's so intimidating when you go back there.
136. Skating into a railing. Don't do that. What? What? It's a robot retrieval on volcano crater. Yeah, no. Anyway. Oh, we got this one again. Yeah, they tweak it a little bit in B. Anyway, so you have an idea there of things you can practice and try, right? Okay. If you don't want to practice, you're like, oh, I don't have time for that. Down here, additional sample problems. It should pop up chapter 8, right? And then, let's see, conservation of mechanical energy along a track. What does that one look like? Oh, look. They're doing conservation of energy problem. I know it's really small on the screen, but you can go, zoom in yourself. So, trying to show you there's lots of resources there for you for that extra practice. And I know it feels like I'm beating you with both hands as opposed to just one when I'm saying, oh yeah, do your homework and do more. But I've watched students do the homework and then continue to rehash the homework. I'm not sure that that's giving you much benefit. Try something else, right? Try applying it in a different context. The more you do that, the better your brain is going to be able to start identifying okay, I really don't know what I'm doing in this work other term. How do now I know I got to go ask a tutor. I got to ask Discord. I got to go ask something, right? And because I'm old, I would recommend that you ask flesh intelligence, not artificial intelligence. Not that the artificial intelligence is bad. It just doesn't know. It can't see the existential dread on your face as you ask the question. One other thing to do is before you start homework in a chapter, before you start homework in a chapter, go to it. Where is it? Chapter 8. Go to the end. Go to the problems, okay? And then you might want to try number 1 and 3 and 5. Why would I encourage you to try these first few odd-numbered problems? They're easier, right? I haven't necessarily assigned the easy ones, okay? I'm picking the 3 or 4 conceptual questions I feel are the best, and then the 8 to 12 representative, again, I'm trying to over-prepare you for the exam type questions. And some of you have had feedback to me, not you personally, but students in the past. Mr. Balogh, you should just give homework problems that are exactly the same difficulty as what's on the exams. I suppose that's fair, but I'd rather you be over-prepared, because I'm not just preparing you for the exams. What am I preparing you for?
4B.
Physics 4B and 4C and the rigor that you're going to be up against in your upper division classes, junior and senior level stuff, right? Okay? Yeah, and those of you that are smiling right now because you don't have to take Physics 4B, me. No. There are some majors that only have to take 4A, which is great. You'll have other problems. Shouldn't say things like this on YouTube. Chemistry is fine. Uh, 1A, 1B, it's fine. Organic chemistry is, I don't understand. Yeah. There's a reason I'm not a doctor, and it's called organic chemistry. All right. What would it be like to see me in the doctor's office as your physician? I'd like run in and start screaming and jumping up and down on tables and wearing my vector hat. Yeah. I am definitely not a brain surgeon, that's for sure. All right. I'd probably like orthopedic surgery I could do. Emergency room. Could do that one. All right. What else? What else can we do in the last 10 minutes here? Write down all the answers. That's Google, right? ChatGPT. It has all the answers. Sit down. Say, pretend you are Mr. Balogh at Fresno City College. Write an exam. No, not going to work. Did we do what? So that's what I call circular motion. Yeah, so it's the loop-de-loops, top and bottom of the loop-de-loops, that sort of stuff. And you had some homework problem. Didn't you have a car going over a hill? Circular hill? I seem to remember something like that. Oh yeah, and then we had the one going around on the top of the table. Yeah, those are all angular motion problems. Yeah. For energy, when do you use the angle and when do you not? When you need to. That didn't help. Come on, come back to me. I know, my face is there. The answer is it depends. So, like, you could have a problem, like somebody's riding on the snow and they get to a flat part, right? And then they kind of come up another hill or something like that, right? Well, there's going to be an angle here, right? So you might need the angle to find the vertical height. Like, what if they tell you that they slide 25 meters up the hill, right? Well, for MGH, H is not 25. What is H? It's 25 sine of whatever that angle is. How did I know it was sine? Well, it's not touching my angle, right? It's like the side of a triangle. So my answer to how do you know if you need to use the angle is, well, geometry. Like understand that for energy, you're putting in MGH. What's H? It's vertical distance that the object traveled. Now, the object actually traveled like this, right? But this only cares about the vertical displacement. However, if we're talking about the friction on the hill, right, where the friction's down like this, right, well, friction, which is going to show up in the work other term, right, negative F times D, we need to know the normal force. Well, the normal force for something on a hill is not mg. What is it? It's mg cosine theta. So again, I'm using the angle again, not because it's the angle, but because I need to know what the normal force is. And the normal force on a hill is opposite to the component of gravity that points into the hill. So yeah, it's not a question of like when do you use the angle? You use the angle when the thing that you're trying to plug in requires it. I wish I could give you a hard and fast answer. It's knowing the way you know is knowing like what this height means. It's a vertical distance, right? Whereas This normal force right here is being opposed by some component of gravity. That's why the angle showed up right there. It's a good question. And again, I know you're hunting for, I want exactly step by step. And I can only give you exactly step by step so far, right? The algorithm works for all the problems, but it's going, the details will switch up. I know you're like, it's the details that freak me out. Yes, I know. So where are you going to learn the details? Practice, 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 practice. If physics were easy, everybody would do it? No? It is always, always worth the fight. The lie is that everything should be easy. And it's just not true. You work hard. You work hard, and that's where the learning happens. Notwithstanding all the rich people in the world telling you that you should skip college and go make your billions of dollars. If that works for you, great. But for the rest of us, we work really hard to get to where we need to go. All right, let's leave it there, right? And tomorrow I have no presentation at all for lab, right? It's literally you come in and get help. Whatever questions you need. It's grasp, right? Finishing up homework, working on cheat sheets together, whatever. Hold on a second.